So at this point, we're going to continue on into chapter 1 about the de Broglie postulate. I never know if I'm pronouncing that one right. It's a French name. And this is something else that happened in the early 1900s as part of the foundations of quantum mechanics. And so in the early 1900s, there was evidence that light behaved both with particle-like properties. So we saw that with the photoelectric effect. And we also know that light behaves like a wave. So there's evidence of both of these happening with light. So for example, under the particle side, like I said, we have the photoelectric effect, where Einstein showed that the only way we can explain the photoelectric effect is if we assume that light comes in distinct packets, in distinct quanta, and so it's behaving like a particle. On the other hand, we have wave effects, things like light diffraction. So if we send light through two slits, it'll interfere, the waves will interfere with each other. And that is something that happens because light acts as a wave. And then also we see a wave-like property is what's known as dispersion, and that's where light is spread out into its different colors. So this can happen in, say, a prism, and this has been observed for centuries at this point. Newton was, I think, one of the first ones to show dispersion. And so light, we can say, has this wave-particle duality. So the question then that was brought up by de Broglie is, well, if light can behave in both of these ways, what about matter? Why not matter? And so that was his postulate, is that matter also can behave like a wave or like a particle, like we're used to thinking of matter. And so what about an electron? Maybe an electron can behave like a wave. So Einstein showed that wavelength and momentum of a photon are related through this equation. The wavelength of a photon is h over p, so that we can say that photons, these particles of light, actually have momentum, p here being momentum, h is the Planck's constant. So de Broglie said, well, matter can behave this way as well. And so if we substitute the definition of momentum that it's mass times velocity, we can say for matter, lambda is equal to h over m times v. So then the question is, why don't we usually observe this with matter, right? So in our everyday lives, we say, like balls and things like that definitely don't diffract, they don't get dispersed, right? We only see particle-like effects in macroscopic world. But let's go ahead and calculate, if we assume de Broglie is right, which plot twist, he is, what are some of these wavelengths that we would observe for these different types of matter? So we'll go through a couple of examples here. All right, why won't it let me move? Okay, so let's take a car. We'll assume it weighs 1,000 kilograms, and it's moving at 60 miles an hour. So let's go ahead and plug that into our de Broglie formula. So we have mass in the units we need, but we need to switch the speed to meters per second. So if we take 60 miles per hour, and it's 1.61 kilometers per mile, and then we can take 1,000 meters per kilometer. So that'll get us to meters, and then we need to switch to seconds from hours. So for every hour, there's 60 minutes, and for every minute, there's 60 seconds. So if we go through all those unit conversions, we get 26.8 meters per second. So we can then plug that into the formula, lambda equals h over mv. H is 6.626 times 10 to the minus 34 joules times seconds. Always remember to include your units. This is really important in all of physical chemistry. If you don't remember your units, you might miss some factors that you need to change. Like, for example, the 60 miles an hour needs to be in meters per second, or else it doesn't cancel with the units that we have here. Then we can put our 1,000 kilograms times 26.8 meters per second. So let's just check our units here. A really, really useful thing to know is that a joule is equal to a kilogram times meter squared over second squared. So if we just look at the units on this equation, if we separate out joules, we get kilograms meter squared over second squared times seconds divided by kilograms times meters per second. So our kilograms cancel, all of our seconds cancel, and our meters cancel. So overall, we'll get units of meters out of this. And so if we plug all these values in, we get 2.47 times 10 to the negative 38 meters. And that is a tiny, tiny value. And so for macroscopic objects, these wavelengths that we're talking about for the de Broglie wavelengths are incredibly small. And so that's why in everyday life, we don't observe things diffracting, right? The wavelengths are just too small for us to actually observe it. Even with, modern scientific instruments, we can't observe, a car or a person or a baseball diffract. We'll see that that's not necessarily true for when we get smaller than that, of course. Let's look at, say, something like, instead an electron. So electrons have much smaller mass, and they generally move much faster. So let's say an electron at 1% of the speed of light, c. So the mass of an electron is 9.109 times 10 to the minus 31 kilograms. The speed of light is roughly 3 times 10 to the 8th meters per second. So we can go ahead and plug this into our same formula here. 6.626 times 10 to the minus 34 joules times seconds, divided by the mass, 9.109 times 10 to the minus 31 kilograms, and our speed is something like 0.01 times 3 times 10 to the 8th meters per second. So if we plug all those values in, we get something about 2.42 times 10 to the minus 10 meters. I would encourage you to check my calculations here, go through this yourself, make sure you understand what it is I'm doing, and that make sure you get the unit conversions that I've done, particularly for the car. So this is still small, right? 10 to the minus 10 meters, but now we're talking on the order of, atomic scale, right? At the time de Broglie postulated this, we didn't necessarily know exactly the scales involved, but now, 10 to the minus 10 meters an angstrom, that's roughly the scale of a single atom. And so this wavelength is on the order of atoms, and we can actually take advantage of this, which we'll talk about in the next video. But this shows sort of what, when we're talking about macroscopic objects, we can't observe this. But for microscopic objects like electrons, quantum mechanical objects, we do observe this, these wave-like properties. And we'll see in the next video some experimental evidence of that.